So back to the point again. In higher classes, we have to study the orbital structure of benzene. In orbital structure, I have explained you like that there is a carbon plane in figure 10.2b. You can see, and in 10.2a also, the hydrogens are also placed in the same plane, and there is a electron cloud above and below it. The pi electron cloud that carbon shares and between two carbons, and because this interaction is between two pi electrons that are neighboring to it, it forms like one and half bond. We can say that this half bond is always having the extra energy that is making benzene more stable. The bond length decrease because the stability increases, and this makes the stability of benzene. And because this is being happen in both the carbons neighboring to it, the bond length actually doesn't become like they it will show a bond length of single bond and then double bond, single bond, double bond. It will show a similar bond length of 1.39 Armstrong between every two carbons in a benzene ring. A benzene is a flat molecule. It is symmetrical molecule. All the parts of it are having all are having what we can say, they are all equivalent. Then a bond angle is 120 degree. Pi orbitals above and below it, and these are the pi orbitals that are making the benzene uh, liable to have an electrophilic aromatic substitution. Then here is the sandwich structure of benzene. The it's like the carbon plane, electron cloud above, electron cloud below, and because of this, the benzene molecule clouds above and below the plane of the ring. This is making the electrons available for reaction. These electrons are available for reaction, and this can help benzene have more stability. And this is the reason why we can say that the delocalization of pi electrons, uh, I will suggest you that delocalization of pi electrons varies is a very simplified statement. uh, there is no actually we should consider that instead of delocalization of pi electrons, we should in mind, in our mental picture, we should consider it as a interaction between two pi electrons are neighboring to it will be same. The delocalization is actually a simplified statement for this, and it will help the beginners to study the benzene. So based on all the study we have done, here is the orbital picture uh, of benzene. The carbon hydrogen bond is 1.10 Armstrong. The carbon carbon bond is 1.39. All the bond angles are up 120 degree, and this makes benzene a symmetrical molecule. These results are based on the analytical studies, qualitative analytical studies that are done, like X-ray diffraction, electron diffraction. Here, then again, I will tell you about the pyridine. The because uh, because nitrogen is having somewhat similar properties to that carbon. The cationation property of that p block elements to some extent makes the pyridine also a aromatic compound. So representation, I have told that there will be two resonating two structures that will be that will be for the electrons will be available in first structure for some time, second structure for some time, and this will go on. And this we can uh, in a very simplified way we can give this structure in the first one that that is shown in the screen. In the in this session, for this session, the last point I am going to teach you is that aromatic character, the Huckel rule of aromaticity of 4n plus 2. So we have, in this rule we have to consider one ring as one nucleus, and this nucleus is denoted by n in this formula, and this is Huckel's formula for aromaticity. In this formula we have to we have to calculate based on the nucleus that are being formed. One nucleus means one ring. One ring is nuclear denoted by one nucleus, and for this, then uh, we can calculate the aromaticity for another uh, multi or polynucleated compounds like naphthalene, anthracene, phenanthracene, and there are also different cyclic structures that another elements can also form, and we can understand the aromaticity in this also. And then what is aromatic character? By Huckel, Huckel told that the aromatic character is like uh, the ring should be planar. The all the carbons or elements in the ring should be in same uh, hybridization state, maybe sp2 that we have seen in carbon. All the carbons are in sp2 hybridized state because of formation of one and a half bonds with two neighboring carbons and one bond with hydrogen, like one and a half and one and a half. Uh, it will be one half, two covalent bond with two neighboring carbons, and one covalent bond with hydrogen bond is also a covalent bond, and these three bonds will make because of the sp2 hybridization. And the here is the formula for Huckel rule, Fn, yeah, 4n plus 2 rule. Then here I will explain the structure. uh, so other than benzene, another structures could also have the aromatic character. We have to consider not based on always on the resemblance of any compound with that of benzene. We should always take in mind the electron cloud method. Then orbital structure, not orbital structure but electron cloud, that it should have electron cloud, so that the stability will be formed, and this stability is based on. Then for the stability, another points are also important that are included in the Kill rule of aromaticity. These are like uh, there should be pi electrons, the pi bond should be there, they should be in conjugation. So two pi bonds should be not directly formed by one carbon to another two carbons neighboring to it. One carbon will form only one pi bond with neighbored carbon. Please don't make confusion for one and a half bonds. I have told you. I am again going with simplified language. So in a cyclopentadienyl cation, cyclopentadienyl radical, cyclopentadienyl anion, you can see this structures on screen. Uh, 4 pi electrons, 5 pi electrons, 6 pi electrons. Based on the Huckel rule of aromaticity, there is only one nucleus, and we can do maths. 4 into 1 plus 2, it will be like 6 pi electrons should be there, so that it will follow Huckel rule of aromaticity, and it will have the extraordinary stability of an aromatic compound. But we can see that there are only two pi bonds in first one, so four electrons. So four pi electrons which are not suitable, and it is not aromatic compound. Second one has 5, it is also not, and the third one is having 6. So this anion is actually having aromatic character. The cycloheptatrienyl cation having 6 pi electrons, then 7 pi electrons in cycloheptatrienyl, then 8 pi electrons in cyclohepta trianiline. And the aromatic numbers are like 6, 10, 14, 18, 22, and we should consider these numbers. And in cycloheptatrienol there are 6 pi electrons, and this is making it aromatic. So we have to consider these characteristics while studying the structure of benzene, chemical reactions of benzene. I will continue this series if I get good response for POC2. Uh, so thank you for this session. This is all. Thank you so much.